Um, Hi, I'm here to present my final project on a toolkit for deep protein structure prediction. It's kind of like in a different style of project, and hope you guys like it. And if you have any questions or concerns, please comment. So basically, protein structure prediction from amino sequence axis, amino axis sequences is a kind of very important problem in many applications for drug design and enzyme design. And currently, the deep learning models are kind of having the state of performance in this task. So it's kind of important to look at the toolkits for developing deep models for protein structure prediction. So a good toolkit, in ideal, would minimize the time of boilerplate protein common functions for this task, and only let you to focus on the model part. So the motivation for me to do this as a final project is actually there isn't any good toolkit out there. So if you look at the open completion for this task using deep learning models, there are others using legacy frameworks which isn't actively being maintained, or they are just not modularized, such that if you wanted to implement a new model, we have to change here and there and to implement functions that are not necessarily helpful for modeling. So to actually define what a good toolkit might be like, so in one simple sentence is that it should be very easy to use. So the code flow for this, using this toolbox to implement the new methods should be roughly wrapped up in a pset. And also it should be very expressive and scalable for really serious experiments such that it can perform heavy-duty jobs. So there are several dimensions of design principles that I considered for this project. So first is that you wanted to use a model framework such that everything is being actively maintained. And also you wanted to have a modularized design such that all your code should be concentrated on the model part and nothing else. And also because the job is intrinsically computationally heavy, you wanted to have a scaling ability such that it can scale multiple machines, multiple GPUs, and you want to have easy-to-use visualizations such that you can debug your model as long as it's training. And also you wanted to have automatic evaluation that you can know where you're at during training, and you wanted to have this mixed precision training, which is something that you can utilize for the current modern GPUs. So if you look at those dimensions, all the current methods kind of lack them in some ways. So I wanted to have a toolbox that have all of them. So I wanted to focus on, instead of going to the detailed mechanisms of implementing them, I wanted to show you the user experience of the four parts that I spend most of the time coding on. So the most important one is the modularized design. So the modularized design allows you to implement the new methods by just replacing four functions in this toolkit. So the four functions are essentially the ones defining the input and output from the data set, and the one that how you actually use the input and output to pass to the network, and the third is to how you define the loss functions for training, and the fourth is the actual implementation of your neural network model. So all you have to do is to implement those four functions, and all the training and bookkeeping of everything is all taken care of. So all the methods I implemented during this project is basically just modifying those four functions. And the code flow for those implementing methods are roughly just 200 lines of code. So here is an example of user experience about scaling to multiple machines, multiple GPUs, and using mixed precision training. So what you have to do is just to pass flags to the training string. So for example, if you wanted to train a model, use tons of machines and tons of GPUs, all you have to do is to pass two flags to your training model, which is basically a multi-part system training, telling that you're actually using a lot of distributed training, and also an IP address for your signal, which does all the communications between signal gradients and weights. So also there's a visualization tool that only depends on Python 3 built-in HTTP server. So all your predicted structures will be automatically dumped into a file. If you use the server, it will actually visualize all your structures in 3D. And because this is a PDF, I cannot show you the live demo of things. So actually, what you see here is the rendered structure of the 3D proteins, and you can actually use your mouse to drag them around to view them in different viewpoints in real time on the web page. So yeah, so that's the basic components that I spend most of the time on. And to demonstrate that they're actually useful, that I implemented to the baseline. So one is called RGN, which is essentially a recurrent network taking input of the sequence and output the 3D structure of things. And the other is called deep contact, which is actually a convolution network, trying to create the pairwise distances between amino acids, between the input amino acids. So I really put in those with the toolkit, and on the above there, sorry, it's a little bit like here. Sorry. So above here is the actual model implementation for those baselines. So if you use the off-the-shelf network blocks, those two methods are actually very, very simple. So they are actually basically, I would say, 30 lines of code to actually implement the neural network models. So if we use that, then we actually train that with the toolbox, and here are the performances on two CESP datasets, which is like the common training and validation sets provided. The validation metric is called ERMSD, which is a metric basically telling you how accurate your predictions are. So the lower the scores, the more accurate the models are. So here the original scores for RGN is better than our re-implementation because they spend more time training and tuning on random seeds, so which is stated in the original paper. Like they actually initialize tons of models with different random seeds and choose the best one. So that's what I observed. So the training is slightly unstable. You have to do a lot of tuning to make it train, but we kind of read the results to some degree. If we have more conditional results and more time, we can reproduce the results fully. But for the scope of the course project, this is the best result that I can get. And for deep contact, they actually train on their custom collected data sets. So I don't actually have a reference score, but if you can compare that with the RGN implementation, and you can see that the toolkit can give you reasonable results. And also, you may assume that maybe this toolkit is kind of overfitting to those two baselines. So I implemented something that's actually new that no one has done this before. It's actually just you use a neural network to actually model the folding dynamics. So what the previous model do is just do end-to-end training in one step. So you input the sequence, output the final structure. So for the folding dynamics, actually the input network is the current configuration of a certain sequence. You output the update vectors of the current configuration. So if you use the modern techniques for some physics model learning, you can actually train this neural network through an ODE solver, such that you can do basically implicit UN solvers and train the neural network in that fashion. So if you do that, you can also have beautiful results on CASP7 and CASP8, but the training is kind of unstable, so I didn't really get really good scores for those. But I guess this is something that actually intrinsically motivates me, and this game3 is actually the original proposal for the final project, but I spent most of the time doing a really good toolbox to make it to explore more efficiently. So I guess this one kind of nicely echoes with the litho paradox of the protein folding problem, which basically states that given all those, because you have tons of degrees of freedom during the protein folding, there must be a really well-behaved energy function that guides the folding process. Otherwise, if you randomly initialize tons of amino sequences, they'll fold into different structures. The fact that they fold into the same structure with high probability means that there is a good well-behaved energy function. So here we're trying to use the network to learn the gradient of this energy function with respect to the current configuration. So hopefully this can be more generalizable to unseen sequences, and hopefully they can perform better as well. So yeah, so in summary, I built a toolkit, experiment with baselines, and implement methods with the toolkit.
So which lectures in the class do you feel that this is the most related to? I mean, of course, we sort of touched upon neural networks, but mostly for genomics, not for proteomics. I'm curious.
Yeah, so yeah, that's a good problem. So I guess it kind of echoes with the RNA coding part, but it's kind of loosely related because it's not so share so much similarity with that. So I guess for me, the reason that I wanted to take the class is actually to do this project. So it's kind of the other way around. Because I don't have a bio background, so actually wanted to know more to at least not be ignorant when I'm doing something related.
What made you choose a protein project?
So this is actually, I think this is computationally interesting. So because you know that there exists this well-behaved energy function, and really wanted to know what that function looks like. Because that's kind of like so this problem kind of being that there is a unknown physical process that you have observations over, but you really wanted to model those complex physical interactions without from first principles, because if you start from the first principles, you have tons of assumptions that you know that you can get past. So yeah.
Isn't kind of the biggest assumption to think that there's a nice function that there's all these like helper chaperones that help proteins fold? Like, what makes you assume that there's a nice protein fold?
So I guess this is more of a thought experiment from really ancient protein folding literature. That they assume that because you think of the amino sequences, they kind of like if you can observe some consistent structure that's the result of folding, then basically the folding is some dynamics that are guided by your energy function. So basically, if you give it a configuration, you can figure out what's the potential function of that. And the folding is minimizing that energy function to a stable state.
I think that's assuming that there's not other parties that are
involved. Right, exactly. Yes. So yeah.
Right. It raises into the whole field, right?
Yeah.
Other questions? All right, thanks again.